All right, this is Business Cal, section 4.1, part 3. And we're talking about a new number, the number E. So imagine that a bank offers 100% interest and that you deposit $1 for 1 year. So we're going to see how the value changes under different types of compounding. So for annual compounding, your $1 would grow to $2, original dollar plus $1 interest. For quarterly compounding, For quarterly compounding, we would use the compound interest formula with P equal to 1, R equal to 1 for 100%, M equal to 4, and T equal to 1. So under those conditions, your $1 would grow to $2.44. So that's an improvement of 44 cents over annual compounding. For daily compounding though, so if we're compounding every single day, the value after a year would be $2.71, which is an increase of 27 cents over the quarterly compounding. Well, clearly, if the interest rate, the principal, and the amount of time stay the same, the value increases as the compounding is done more frequently. So in general, if the compounding is done M times a year, the value of the dollar after a year will be 1 plus 1 over M to the M power. Well, if you take that generic formula and plug in different values of M, making that compounding more and more and more. So looking at slide 24, we start at 1 time a year, which got us to our $2. If we up that to 4 times a quarterly, we got $2.44. If we upped it to daily, we got $2.71. What if you upped it to 10,000 times a year? We get 2.72. What about 100,000 times? It's growing. Still growing. Not growing as quickly, but still growing. What about 1,000,000 times? Again, still growing. And 10 million times. Again, still growing, but you can see that to 5 decimal places, the difference between 1 million and 10 million didn't really change. So the more that we're compounding per year, okay, if we get up to 1 million, at some point it's going to level out, and this one leveled out at 2.71828, or about $2.72. Okay? Well, what does that mean for us, and why do we care? So looking at slide 25, you notice that as M increases, the values in the right-hand column seem to be settling down to a definite value, and that value is 2.71828. So that is as M approaches infinity. Okay? So as the limit as M approaches infinity of the function 1 plus 1 over M to the M power. Okay? It's getting to 2.71828. Well, this particular number is very important in mathematics and is given the name E. Okay? So this is E. This is just as 3.14159 was given the name pi. Okay? So we have E and we have pi. So, in the following definition, we're going to use the letter N to state the definition in its traditional form. So E is equal to the limit as N approaches infinity of the quantity 1 plus 1 over N to the nth power. And that's 2.71828 ... The dots mean that the decimal expansion continues to go on forever. So, the same E appears in probability and statistics, in the formula for the bell-shaped or the normal curve. So if you've already taken business statistics, you should have seen this formula. Its value has been calculated to several million decimal places, and its value to 15 decimal places is given here. Okay, Your calculator has an E button, and that's what we're going to use the most. Okay, but knowing where this number comes from and how it's given or how it was found, okay, this was a number that was found. This pattern showed up so often, and it showed up every single time in the exact same way. They gave it a number, or they gave it a name. Okay, it's not just a number that somebody created. Well, how are we going to use E? Where does it help us? Okay, well, we've talked about compounding daily, monthly, quarterly, annually, semi-annually. But what happens if I want to compound more than that, and I want to see what happens if I'm compounding continuously and continuously going through? And that's where the 1 million times a year, 10 million times a year would come in. If we're continuously compounding, what we get is a formula called continuous compounding. So this kind of compound interest, the limit as the compounding frequency approaches infinity, is called continuous compounding. And what we've shown through the table is that $1 at 100% interest compounded continuously for a year would be precisely worth E dollars, or about 2.72. Sorry. So the formula here that we get to replace, remember, E is equal to the limit as n approaches infinity of 1 plus 1 over n to the nt. Okay? Well, what we get to do is take all of this stuff here and take our original compounding interest formula, and all the junk in the parenthesis gets replaced. And what we end up with is, for continuous compounding, that value after so many years is P e to the RT. Okay? Where P is still that original amount that you invested. Your R is still your rate. Make sure you're changing that to a decimal. And T is however many years we're dealing with. So, take a second, pause your video, and find the value of $1,000 at 8% interest compounded continuously for 20 years. All right, so if you take and plug in your different values, we should end up with $4,953.03. Okay? Again, as you're reading through your problem, make sure that you're marking down what numbers or what variable, and that will make this entire process go a lot more efficiently and a lot quicker. All right, so this again would be your future value. If you put 1,000 in now, what will I get in the future? Well, just like before with our other compounding formula, if you know if you can find the future value, you could also find what we called that present value. And it's the exact same concept. We're going to take whatever amount of money we want to get in so many years and divide by that e to the RT. We do have another option here. Instead of dividing by e to the RT, remember this is just an exponential function, I can move the e to the RT up by adding a negative exponent. So you have two options. I tend to just keep with the division because that helps me keep it straight in my head, but it wouldn't matter. So PE to the RT would find that present value if I know what I need in the future to figure out what I need to put in now. Or you can do P times E to the negative RT. And it's just that rule of exponents that if you're pulling something up from the denominator, we have a negative exponent. Both work. Both are correct. Again, I tend to keep it with division just so I can keep it all straight. All right, let's keep going. So if we want to find the present value of $5,000 to be paid in 10 years at 7% interest compounded continuously, we know that we want to find that present value. So we have 5,000 divided by E to the E to the 0.07 times 10. All right, so take a second and put that in your calculator. All right, you should get 2,482.93. So if you know in 7 years you need $5,000 and that's the account you can find, you know you need to put in $2,482.93. All right, so let's keep going. So under quarterly compounding, your money is, in a sense, earning interest throughout the quarter, but the interest is not added to your account until the end of the quarter. But under continuous compounding, that interest is added to your account as it's earned with no delay. So you have extra earnings. Extra earnings in continuous compounding come from the instant crediting of interest, since then your interest starts earning more interest immediately. Okay, so you're getting more interest at a quicker rate. All right, so how do you compare different interest rates, such as 16% compounded quarterly or 15.8% compounded continuously? If you needed to compare those, what you're going to do is you're going to deposit $1 for 1 year. Okay, so you'd have two different accounts. You've got one where your P is equal to 1. Your rate would be 0.16. We know our M value would be 4. And my time is 1. Or for your second account, we would have, again, $1, interest rate of 0.158. We don't have an M value because we're compounded continuously. So we know we're going to use E. And again, your time frame is 1. So you need to figure out what's going to give you the better interest rate between those two accounts. All right, so I want you to pause the video and find which is going to give you that better interest rate given these two things. You're going to plug it into two different formulas. Okay, so the first one you'd plug into P times 1 plus R over M to the MT. And for the second one, that A equals PE to the RT. All right, so pause the video, plug both of those in, and then come back and see if you got the right answer. All right, so our first account, the 16% compounded quarterly, would give us an interest of $1. It looks like $1.17. Okay, but if you take the decimals out a little more, we got 1.1699. And your second account, that 15.8% compounded continuously, gives us an interest of 1.1712. There's not a huge difference between these two. But if you think about it in the long run and for larger numbers, okay, the compounded continuously is going to give you a better return on that investment because for $1 we had more interest. Okay, so that's how you would compare the two. $1 for 1 year. All right, so we'll finish this section in the next video.